project is Soil Analyzer. So why soil analysis has paramount importance? After Kerala floods in 2018, it's reported that the soil texture in cultivating lands has undergone drastic changes, which is mainly in the topsoil. And studies have shown that the production levels of various crops have declined significantly in 2019 when compared to the previous years. Researchers clearly mention two reasons for this huge loss from a crop yielding state like Kerala. The main reasons are failure in proper analysis of soil before soil cultivation, and secondly, lack of knowledge in farmers about the soil pattern and the type of crops cultivated. The main aim of our project is to design a portable device which has the following features. Have features to collect soil samples from different parts of a given land, and these samples are checked for parameters that are important in the crop production. These parameters are NPK, which is nitrogen, phosphorus and potassium, the pH of the soil, the humidity and moisture of the soil, and also the temperature of the soil. The movement of the device is managed by chain wheels that makes the movement in all terrains possible, which means that even in rough terrains, the vehicle can move smoothly. Navigation is managed by integration of ultrasonic with GPS module. The collected data values are cross-checked against the threshold values in the database and given proper information about the types of crops that are suitable to be cultivated in a particular region. The information can be properly channelized by an app so that the idea is rightly conveyed to the farmers or the landowners. What makes our project stand out is that it can instantaneously give the value of the soil rather than waiting for the result to come from an agricultural office. So the soil doesn't have to be taken to the agricultural office and waited for the result to come out. The values can be instantaneously found. So this is the layout of the solar analyzer. It mainly contains the rover body and the chain wheels are attached to it. Chain wheels are used so that movement in all terrains are possible, so that even in rough terrains the vehicle can move smoothly. In front of the device we have a solar panel attached to it. The solar panel is used to power the device. Next to it we have the drill bit. The drill bit is used to loosen up the soil when the sensors are inserted so it can be easily inserted. Adjacent to that we have the sensor cylinder in which all the sensors are integrated together. These sensors are pH sensor, DHT11 sensor, moisture sensor, temperature and humidity. Next to that we have the power and control. The device is placed on the ground in which the soil parameters has to be measured. Once it's placed, it moves to different parts on the ground. When it reaches a particular position in which the measurements has to be taken, it stops. And then the drill bit is inserted to the ground to loosen up the soil. Once the soil is loosened up, the vehicle as a whole moves forward in a fixed delay, such a way that the sensor cylinder comes in the position where the drill bit was before. After this, the sensor cylinder is inserted to the ground and the measurements of the soil parameters are taken. These parameters are compared to a threshold value and the result is calculated. These results are sent to the farmer via an app. And then here we get the values of the soil instantaneously. So this is the layout of the soil analyzer powered by solar panel.
The general block diagram of the soil analyzer is as below. The Raspberry Pi 3 Model B forms the heart of the system. It consists of a 1.2 GHz 64-bit quad-core processor with built-in Wi-Fi, Bluetooth, and USB boot capabilities. Audio output, camera port, USB ports, HDMI outputs are also included. The biggest advantage of Raspberry Pi over Arduino is that multiple codes could be run at a time, thereby enabling multitasking. It is powered by a 5-volt micro USB supply. Coming to sensors, there are 4 different sensors that are used in this project. They are 1. DHT sensor, 2. Moisture sensor, 3. pH sensor, and finally NPK sensor. Coming to DHT11 sensor. DHT11 is a basic low-cost digital temperature and humidity sensor which provides humidity and temperature values serially with one-wire protocol. It uses resistive humidity measurement component and NTC temperature measurement component. It provides relative humidity values in percentage ranging from 20 to 90% and temperature values in degrees Celsius ranging from 0 to 50 degrees Celsius. DHT11 is a 4-bit sensor. The pins are VCC, data, ground, and one pin which is not used. The VCC is connected to the power supply of the Raspberry Pi, the data pin to the digital output pin, and the ground pin is connected to the ground pin of the Raspberry Pi. Soil moisture sensor. The FC28 soil moisture sensor measures the volumetric content of water in soil, which is achieved indirectly by using other properties of soil such as dielectric constant, electrical resistance, etc. It consists of 4 pins: the VCC pin meant for power, the AO pin meant for analog output, the DO pin meant for digital output, and the ground pin which is connected to the ground of the Raspberry Pi. The module also includes a potentiometer that will fix the threshold value, and the value can be evaluated by comparator LM393. The LED will turn on or off based on the threshold value. Specifications: working voltage is 5 volts. The current needed for working is less than 20 mA, and the type of interfacing is analog in nature. Working temperature is 10 to 30 degrees Celsius. For interfacing moisture sensor to the Raspberry Pi, the MCP3008 IC is used, which is a 10-bit 8-channel analog to digital converter. Coming to pH sensor. pH refers to the concentration of H+ ions in the solutions. The parameters for pH sensor are working voltage 5 volt, measuring range 0 to 14, where 7 represents neutral, 0 to 7 represents acidic, and 7 to 14 represents basic. Accuracy is plus minus 0.01, and the response time is less than 1 minute. The pH sensor interface is provided by the B and C. The pH sensor contains two electrodes, a sensor electrode and a reference electrode. These electrodes are in the form of glass tubes. One contains pH 7 buffer and the other contains saturated potassium chloride. A silver wire coated with silver chloride is immersed in pH 7 buffer in the bulb. When the probe is placed in a solution to measure the pH, hydrogen ions accumulate around the bulb and replace metal ions from the bulb. This exchange of ions generates some electric flow that is captured by silver wire. Voltage of electric flow is measured by pH meter by converting it into pH value by comparing generated voltage with reference electrode. Last but not the least, NPK sensor. Teralytic sensor is the world's first sensor for NPK measurement, which consists of single sensor with 26 sensors reporting soil moisture, salinity, and NPK at three different depths as well as aeration, respiration, air temperature, light, and humidity. However, it is highly expensive and costs around Rs 10,000. Hence, for the purpose of this project, we are using test signals. The values collected from different sensors are then given to a cloud where it is compared with an already existing database containing optimum values of various crops, thereby serving the purpose of determining which crops needs to be cultivated in a given land with the obtained parameters. The next block diagram represents interfacing of various motors for movement of rover as well as the linear downward motion of drill bit and sensor assembly. The chain wheels of rover are powered by DC geared motors. The specifications of DC geared motor is as follows: operating voltage 3 to 12 volt DC, RPM approximately 100, output torque 4 kg centimeter. L298N functions as motor driver, which consists of dual H-bridge configuration that allows speed and control of two DC motors at the same time. It can drive DC motors that have voltage in the range 5 to 35 volts. Mini motors are also used for linear downward movement of sensor and drill bit. Ultrasonic sensors are used for obstacle detection, which will be discussed in detail later.
The plan is divided into three phases. Phase 1 covers 30 to 50% of the project. 30% of the project mostly involve researches on sensors, wheels, and rover. We also decided on using the four sensors, which is a moisture sensor, pH, DHT, and NPK sensor. Chain wheels was chosen to provide normal terrain motion. Moisture, pH, and DHT sensors was also implemented using Arduino. In the 50% of the project, we came up with the basic design of the rover, which included the chassis, wheel, chain, etc. A two-dimensional model of the rover was designed using AutoCAD software. Different sensors was integrated to a cylindrical structure. We also studied about the movement of chain wheels. Phase 2 covers 75% of the project. This includes the converting of a two-dimensional model to a 3D model using CATIA software.
The model parts were all 3D printed, including the wheels, chassis, chain, and other parts required for the rover. Also, all parts for the working of the drill bit, that is the screw, frame, screw thread, etc., will also be 3D printed. The printed parts will then be assembled in order to form the complete rover. Coming to phase 3, it covers the remaining part of the project that we hope to complete. This includes the implementation of linear and rotational motion of the drill bit and the sensor unit. Also, an application will be developed for providing the sensor readings. The power requirements of the entire rover, including the movement of the wheels, the linear and rotational motion of the drill bit, and the sensor module, powering of the Raspberry Pi, etc., will be calculated and implemented. This also includes all final programming and processing. The diagram gives the side view of the rover concentrating on the positioning of the drill bit and the sensor unit. Considering the forward motion of the rover, the drill bit will be placed first, followed by the sensor unit at a particular distance from each other. The rover makes a stop at a required point and drills a hole. It then continues moving forward and then makes a second stop when the sensor aligns with the hole already made. This is done by providing the right time delay between the two stops. Within this delay, the distance between the drill bit and the sensors will be covered. It then inserts the sensors and takes the required readings from the soil. There are two types of motions required for this. The first one is the linear motion and the second, rotational. The drill bit undergoes both linear and rotational motion, whereas the sensor module requires only linear motion, which is basically the inserting and the lifting of the sensors. In order to provide the required motion, a rack and pinion gear will be used. It basically converts rotational motion into linear. It has two important parts, that is the screw shaft and the screw thread. The screw shaft will rotate through a threaded hole or a threaded collar. A simple example for understanding this is a nut rotating around a screw. When the motor is powered, the screw shaft attached to the motor starts rotating. The shaft will be rotating through a threaded hole, converting the rotational motion to linear. This enables the inserting and the lifting of the sensor and the drill bit module. The 3D printing process builds a three-dimensional object from a CAD design. The material that we chose for 3D printing was PLA. PLA was chosen as it uses much lower printing temperature and is also a biodegradable material. Our rover design consists of 7 parts, that is the main body, the cog, inner cog, outer cog, tracks and the track midframe. The cog is basically the wheels of the rover and the track forms the chains that runs on the wheels. We will need almost 26 tracks per side. The tracks are joined together by stainless steel pins. Two 9-volt rechargeable cells allows more than 30 minutes of runtime.
DHT11 sensor interfacing with Raspberry Pi. The 3 pins of DHT11 should be connected to the Raspberry Pi as the first pin of DHT to the first pin of Raspberry Pi representing 3.3 volt, pin number 2 of DHT to GPIO 17, that is 11th pin on the Raspberry Pi representing data out. The third pin of DHT is not used. The fourth pin of DHT is connected to pin number 6 or 9 of the Raspberry Pi representing ground. The DHT11 requires a specific protocol to be applied to the data pin. Hence, it is easier to use the Adafruit library. It deals with the data that needs to be exchanged with the sensor, but it is sensitive to timing issues. Software setup. The software setup involves 3 main steps. To start with, update the package list and install a few Python libraries. The second step, clone the Adafruit library from repository. And finally, install the library for Python 2 and 3. The code is as below. First step involves importing the Adafruit library. Next step involves specifying the sensor type. It could be DHT11, DHT22 or AM2302. In the next step, GPIO pin is specified. In this example, we are using GPIO 17 that corresponds to 11th pin on the Raspberry Pi. The read-retry method is incorporated, which will retry up to 15 times to get a sensor reading. The validity of the reading must be checked as DHT11 is very sensitive to timings and occasionally the Pi might fail. The figure represents the result we have obtained by interfacing DHT11 sensor with Raspberry Pi. Moisture sensor interfacing with Raspberry Pi. The MCP3008 is an analog to digital converter. Since the Raspberry Pi cannot detect intrinsically analog signals, we need a converter like MCP3008. Software setup. In order to be able to address the MCP3008, the SPI must be activated. Next, we need to install the SPIDAV library. The NumPy library is also required in order to convert the output value to a percentage. Output values we receive from MCP3008 will be in the range 0 to 0123. We will then map these values to 0 to 100 for a percentage.
Up next, we have the process of 3D printing. As in previous slide, we've already discussed in detail, the parts of the rover are separately fabricated in two different labs which uses different nozzles for the same. In the upcoming video, we show how the process is done. As I told, the rover is made in parts and this is how it looks like after assembly. A few more parts are remaining and that will be done later. Coming to the motion of the rover, we consider two different types of floats, a smaller field and a larger field. For smaller field, we consider movement based on ultrasonics and obstacle detection. While rover moves, it has to consider the object in front of it. Then it has to detect it, and after deviating from the obstacle, it has to come to the same path. Here we speak about ultrasonic sensors. Most commonly used ultrasonic sensor is HC-SR04. Hence, we have used the same. The main principle behind working of ultrasonic sensor is to note down the time taken by sensor to transmit ultrasonic beams and receiving ultrasonic beams after hitting the surface. The trick pin of HC-SR04 is made high for at least 10 microseconds. A sonic beam is transmitted with 8 pulses of 40 kHz each. The time taken by the beam to return back is saved in a variable and converted to distance using appropriate calculations like distance is equal to speed into time, where we are considering speed of sound in air. We have tried to implement this obstacle detection in a small RC rover car, which is demonstrated in the next slide. We've hard-coded its motion by programming it in Arduino. For a smaller field, say a rectangular plot, we consider 4 edges to be the obstacles. On sensing this edge, the rover takes a turn. This is how we have started working on navigation. Later, a GPS module is added, which will remain inactive in smaller fields. On combining ultrasonics and GPS, we hope we shall meet our purpose and requirements of the rover. This is a picture of our RC rover car, which is now implemented with a single ultrasonic sensor and an Arduino. This is another snap of RC rover car. Coming to the code, first we shall define the motor pins. That depends on how many motors that we're using. Here we've already defined 4 motor pins. In void setup, we shall define input and output pins. Motors are connected to the output pin. Trigger pin is also considered to be an output pin. Echo pin is an input pin. In void loop, we talk about a pulse which is to be given to a trig pin. A pulse will be defined by a signal which will be low for 2 microseconds time and then it will go high for 10 microseconds time. So this is the pulse which is given to the trigger pin. After hitting the obstacle, the returned pulse will be coming to the echo pin which will be high. From that, we will calculate the distance using the time duration. This loop is basically for obstacle detection. It says that if the distance is less than 10, the motors will go off and it will delay there for 2 seconds and it will go right. Here, if there is no obstacle, it will move forward. Rest of the code is written to show how the motor is programmed. In the next slide, we will show the demo of the RC rover car.
Okay.
Currently, we are working on GPS module. To begin with, we have chosen Arduino to interface this GPS module. And our next target is to integrate this GPS module with the ultrasonic sensor so that we can use our rover in a larger field. Now I shall explain a pattern for motion. Consider ABCD to be a big rectangular plot. A, B, C and D are considered to be target locations or waypoints which is provided by the GPS module. Consider our initial position A and the rover is placed there. It has to move from A to B, and while navigating from A to B, it might face so many obstacles. So by integrating 2 or 3 ultrasonic sensors, it is possible that we can cover up those obstacles and it can aim towards the target location which is provided by the GPS module waypoints. This is how our strategy works. So this is the overview of our project. The remaining work that we have is about integrating sensors, motors and chain drives. Later, we are planning on developing a web application for proper information management and making the information available to farmers through a proper channel.